2.7, finding patterns. 1869, Dmitri Mendeleev noticed that certain groups of elements had similar properties. At this point, they had discovered a number of different elements, but they didn't have our periodic table. They were still, trying to figure out how to organize all this information. What he did was he put elements in order of increasing mass and noticed that there was a recurrence in the properties. They recurred in a periodic pattern. So the periodic table, periodic refers to exhibiting a repeating pattern. This is something that happens periodically. Now that period could be, every year, every week, or every 8 elements. So he summarized his observations in the periodic law. When elements are arranged in order of increasing mass, certain sets of properties recur periodically. So here we have the first 20 elements on the periodic table. And we find that element 2 and element 10 and element 18 have some properties in common with each other. And element 3 and 11 and 19. And the purple ones here have things in common with each other. It's a little bit like a piano keyboard where you have middle C and then you have C above middle C and then another octave up there's another one, and those are all harmonics of the same note. It's a little bit like that. So he took the elements that were known at the time and arranged them into a table, because one long line like that wasn't so very useful. He made the rows so that elements that had similar properties fell into the same columns. So he took this list here and made it into a table. And now we see that lithium, sodium, and potassium are in the same column and they have similar properties. Helium, neon, and argon are in the same column. And you might wonder, well, why is hydrogen over here? Hydrogen is the smallest element, and he's a little bit like the youngest child in a family. They somehow managed to break all the rules. Have you had that experience? The youngest kid gets away with stuff that as an older child, I was the oldest, I never would have gotten away with doing that. But hydrogen does, and so hydrogen wants to be over here, and so we let him, even though we know that in some ways he should be over here next to helium. The table that Mendeleev made had some gaps in it. And he predicted that elements would be discovered to fill in those blanks. He even predicted the properties of those elements. He predicted an element he called eka silicon. Eka is just a prefix that means below. So it would be below silicon in the periodic table. And sure enough, in 1886, it was discovered by a German chemist who named it germanium after his home country of Germany. This is an interesting version of the periodic table showing times of discovery. So in the light blue, yeah, it does look light blue up there. These are things that were discovered before 1800. And the slightly darker blue, between 1800 and 1849. So all of those bluish elements were known about when Mendeleev was making up these patterns. And here we see there's silicon and here's germanium. And germanium is one of the ones that Mendeleev predicted would be discovered. And this is how, in 1869, Dmitri Mendeleev completed his first periodic table. Nobody? Have you ever played Tetris? See, you've got to rotate this around and it's got to fall right in there. Here's no fun. This is my day. In the modern periodic table, it's not the mass that we order them by, but increasing atomic number. Do you remember what atomic number is? Number of protons. Okay. There's actually a couple of places where if you go in order of increasing mass, you do not have increasing number of protons. And then, of course, our modern table has more elements in it because more have been discovered. In fact, just this past year, several of the newest ones were given official names. So here is a modern periodic table showing some of the divisions and some nice pictures of some of them. Okay, so we need to know some things on the periodic table. Here we have color-coded the metals, the metalloids, and the nonmetals. So there's this dark stair-step line here bordering these purple elements. That's the division between metals and nonmetals. The upper right corner of the periodic table, these elements are all nonmetals, and to the left and below this stair-step line, these are metals. Along this line, most of the elements that actually touch that line are called metalloids or semi-metals. They're kind of like a nonmetal and they're kind of like a metal. So they're semi-metals or metalloids. The exception there, the one you need to remember, is aluminum. Now, we have aluminum around us, right? My soda can here is made out of aluminum. Is it a metal? Yeah. So we should remember that aluminum is a metal. So aluminum is a metal, but the rest of these purple ones are semi-metals. Sometimes students wonder about these guys. You know, why are they stuck down here? These elements really should be up in this gap. We should take a pair of scissors and cut the periodic table right here and split it open and stick these rows up in here, because here we have 55, 56, 57, 72. No, it should go 57, 58, and through here 71, 72. These guys are pulled out because it makes the table too long to fit on a screen or on a nice piece of paper, and we don't use those guys very often. And so they're just kind of stuck at the bottom. These are called the lanthanides because they come after lanthanum. And these are the actinides because they come after actinium. And we're not going to do much with those. So we classify elements as metals, nonmetals, or metalloids, and you should be familiar with some of the characteristics of these broad categories. Metals tend to be good conductors of heat and electricity. They are malleable and ductile. Malleable means you can pound them into a sheet. Ductile means they can be drawn into wires. Nonmetals can't do that. They are often shiny and they tend to lose electrons when they undergo chemical changes. The nonmetals tend to be poor conductors, not ductile, not malleable. They tend to gain electrons when they undergo chemical changes. Bless you. Then the metalloids have mixed properties. Several of them are classified as semiconductors because they have an intermediate electrical conductivity. They don't conduct as well as metals, but they're not non-conductive, and their conductivity is highly temperature dependent. And you've probably heard of semiconductors. Silicon is one of them. Semiconductors are very useful in computer chips. Other divisions in the periodic table are the main group, the transition elements, and then we have periods and groups. So the main group elements on this table are shown in yellow. So we've got these two columns over here, and then we've got this block over here. So you should be able to identify if something is a main group element or not. So there's the main group elements in the yellow. Those are the columns that stick up higher. And then this part down here, those are the transition elements. Main group elements have more predictable properties. The transition elements tend to be less predictable. The transition elements are a transition between this side of the periodic table and that side. And we have groups and periods. So the periods are rows and they're numbered. So this is row 1. It's just hydrogen and helium. And here's row 2, 3, 4. So there's 7 periods. And then the groups. So this is a group number. The groups are the columns. So this is group 1A or group 1. This is group 2A or 2. So you'll notice that all of the groups have 2 numbers. There's the International Union of Pure and Applied Chemistry's recommended numbering, and then there's the current U.S. numbering. Since we're currently in the U.S., I prefer the U.S. numbering, and that's the ones with the letters. They are on this periodic table on the wall in Roman numerals with the letters, and those are the ones I'm generally going to be referring to. So groups 1A, 2A, 3A through 8A. we won't really refer to the group numbers for the transition elements. But remember that elements in a group, in a column in the periodic table, have similar properties. Some of the groups have names. Others are just given a number. You need to know the names of these particular groups. Group 8A, those guys are called the noble gases. They are very unreactive. Several of them have no known compounds. They just don't react with anything. The alkali metals are the metals in group 1A, and they are all very reactive. The next group over, group 2A, those are called the alkaline earth metals. They're fairly reactive, but not as reactive as the alkali metals. And then in group 7A, we have what are called the halogens. And those are very reactive nonmetals. Your book talks about each of those groups, but you can read that. You don't need me to explain that to you. So we said that metals tend to lose electrons. Those main group metals tend to lose electrons. When they lose electrons, they form a cation. And they'll form a cation that has the same number of electrons as the nearest noble gas. Those are the main group metals. The main group nonmetals tend to gain electrons, and they're going to form anions with the same number of electrons as the nearest noble gas. So there's something special about the noble gases. And we'll learn more and more about that as we go through the semester. I think I've got a periodic table coming up. Yeah, we'll look at the table in a minute. The alkali metals, group 1, have a tendency to lose 1 electron, form a 1+ ion. So the group 1A metals have a +1 charge. The group 2A metals tend to lose 2 electrons and have a 2+ charge. You see a pattern there, group 1 +1, group 2 +2. Not too hard. The halogens are in group 7A. Those are nonmetals. They tend to gain an electron. They form 1- ions. And group 6A, which doesn't really have a name, we'll call it the oxygen family, they tend to gain 2 electrons. So for the main group elements that form cations with the predictable charge, the charge is equal to the group number. The group 1A's form +1, the group 2A's form +2. For the main group elements that form anions, the nonmetals form negative ions. Their charge is equal to the group number -8. And I'll show you another way to remember that too. Those transition elements are pretty unpredictable. Some of them form 2 or more different ions. And so those are not as easy. So here are elements that form ions with predictable charges. It's easier to talk about all this with a periodic table to point at. So these elements are in group 1A. Now hydrogen is not an alkali metal because it's not a metal, but it is in group 1A and it does form a +1 ion. So all these guys form +1 ions. In group 2A, they form +2 ions. Aluminum over here is a main group metal. In group 3A, it forms a 3+ ion. The noble gases do not form ions, period. The halogens in group 7A, as the hydrogen, squirrely little guy, he likes to break all the rules. He can also form a negative ion, so in some ways he belongs in group 7A. But here are the halogens, fluorine, chlorine, bromine, iodine. They form -1 ions. So there's 2 ways to remember that. You can take the group number and subtract 8. So the group number is 7, subtract 8, that gets you -1. Or what seems to work a little better is, kind of like playing a stupid board game, and you're starting at the noble gases and then you count backwards. Counting backwards would be negative, right? So you're starting here, and you want to know the charge on fluorine, you count back 1. -1. You went back 1. -2, -3. It's the same result as group number -8, but easier to remember. So these elements in group 6A are going to form 2- ions. In group 5A, they're going to form 3- ions. I really don't know why they don't include phosphorus in here, because phosphorus is pretty predictable. So phosphorus, guess what his charge would be? -3. And you might wonder, well, what about group 4? Group 4 doesn't really form ions much, so that's why it doesn't show up there. You don't need to remember that, but we're just not going to run into them. Any questions? So we should be able to predict the charge of ions by looking at the periodic table. So nitrogen. What charge would nitrogen have? We find it on the periodic table, and then we need to know if it's positive or negative. It's going to be negative. It's a non-metal. It's a negative ion. Okay, they both start with N. Metals become positive ions. So we've got a non-metal, and we want to know the charge. It's going to be negative, so start over here with neon and count backwards. 1, 2, 3. So the charge would be -3. If we're going to write the formula for that, we always write the number first and then the charge, and we always include the charge. It's a little different than exponents. And I think the reason it's different than exponents is we don't want that to be confused with an exponent. We want to be clear that this is nitrogen with a 3- charge. We don't want it confused with the variable capital N raised to the -3rd power, right? Because that would be math. So math would look like this. That would mean 1 over N cubed. But that's not what we're doing. This is chemistry talk, and that's math talk. How about rubidium? Yeah, it's down here. It's in the first group, and all of these guys form +1 ions. It's the same as their group number. So rubidium forms a +1 ion. And so we're going to write rubidium plus. We'll see as we go throughout the semester that chemists seem to have a bias against actually writing the number 1. We leave it off all over the place. And this is no exception. So with positive charges, we do write the plus sign. On an exponent, you wouldn't do that. You would just write the number. But we don't write the number 1. Any questions?